So in a mixture of gases, each gas literally behaves as if it's the only gas that's present, okay? And that's kind of bizarre, but its particles will contribute to the overall pressure, but it behaves again as if it's the only gas in the mixture, and we can determine the behavior of each component in the mixture separately. And we've looked at, and we just talked about this sort of in studies conducted by adding water vapor to dry air. John Dalton was the first person to characterize this behavior in gas mixtures, and that was back in the early 1800s. Anytime you hear the name John Dalton, you think atomic theory. He was the guy that made developed the atomic theory, and you know that was around 1800. So that's a little over 200 years ago in this case. Studies conducted by adding water vapor to dry air. Dalton was the first to characterize this behavior, and he found that the pressure of humid air equaled the pressure of dry air plus the pressure of the added water vapor. So he literally took a container of dry air and measured the pressure of it. And he took a container of water vapor and figured out what the pressure of that was, and then put them together and found out what the combined pressure was. So Dalton concluded that each gas in the mixture exerted a partial pressure equal to the pressure that it would exert by itself. And Dalton's law of partial pressure states that in a mixture of unreacting gases, why would these have to be unreacting? What could happen if they reacted? What might change?
Would it be
solids or liquids?
What's that?
They could
their state of matter change?
Well, you could get a state of matter change, but
Would it be temperature?
could change the temperature, yeah.
Could it react with that container?
It could potentially react with the container, although that's not very likely. But what else could it change? The number of what?
particles.
Change the number of particles, right? Remember, our chemical reactions oftentimes involve a change in the number of particles. On the reactant side, I might have 7 moles of gas. On the product side, I might have 9 moles of gas. So in a mixture of unreacting gases, the total pressure is the sum of the partial pressures of the individual gases. Okay? So if we know this, and we know that we're going to keep a constant temperature and volume, as you add more gas, if P increases as you add more gas, you're going to find out that the total pressure equals these partial pressures of A, B, and C. And this is going to, again, we're keeping temperature and volume constant. So the only thing that's changing is I'm adding more particles, and therefore I'm also increasing the temperature or the pressure of these things. I'm increasing the pressure as I'm adding more particles. And we just got this by dividing PV equals nRT by V, right? PV equals nRT. If I divide by V, V goes over to the other side and just leaves the P by itself. And so what I can also say then is that I can factor out the RT over V and or factor out the numbers of particles, and I can say that the total number of particles or total moles of particles times RT over V is going to equal the total pressure. Okay, so we'll see if I can keep this with power long enough to do this. All right, what happened? It's interesting that that would do that. Okay, So mixtures of helium and oxygen can be used in scuba diving tanks to help prevent the bends. For particular, and what is it that causes the bends? Do you have any idea? Do you know what the bends is? Yeah.
Doesn't it have to do with the like nitrogen bubbles in your blood?
Yes. So if you stay underwater for a period of time, the pressure underwater is going to compress the nitrogen in your blood. And when you come back up, that pressure is going to be lessened, and the nitrogen will come out of solution and cause significant pain as it sort of blocks a bunch of little blood vessels in your body. And we can prevent this by increasing the amount or decreasing the amount of nitrogen that's actually in our blood by adding helium into the air that we breathe. So mixtures of helium and oxygen can be used in scuba tanks to help prevent the bends. For a particular dive, 46 liters of helium at 25 degrees Celsius in 1 atmosphere, and 12 liters of oxygen at 25 degrees Celsius in 1 atmosphere were pumped into a tank with a volume of 5.0 liters. Okay, so we want to calculate the pressure of each gas and the total pressure. Okay, and so we can calculate the partial pressure of each gas, and we'll symbolize the partial pressure of the particular gas by using pressure with a subscript of whatever that gas is. And I know that the partial pressure of that gas is going to be equal to the number of moles of helium times R times T over V. Okay, and so now I have to figure out how many moles of helium that I actually have. Okay, I have to figure out how many moles of helium I actually have. And how am I gonna do that? I'm gonna figure out how many moles of helium that I have. Okay, have I been given the ability to do that here? I've got a pressure, I've got a temperature, and I've got a number of liters. Okay, so this is different than the second situation, right? This is a completely separate situation. I can figure out how many liters I have, or how many moles I have. Remember, PV equals nRT, so N is going to equal PV over RT. And so my pressure in this case is 1 atmosphere, and I've got 46 liters, and I've got 0.08206 liter atmospheres per degree or per mole Kelvin, and I've got a temperature of 25 degrees there, which is 298. So I'm going to have to figure out how many moles of helium I have. So 46 liters divided by 0.08206 times 298. So I get 1.88 moles. Okay. So if and what's the only thing I'm really changing here when I pump this into the tank? I'm only changing the volume, right? I'm changing it from 46 liters to 5 liters. So I guess I'm wondering if I really needed to find the number of moles. Let's see if it works out to be the same though. So I've got 1.88 moles times 0.08206 liter atmospheres per mole Kelvin times, my temperature's still the same, right? They didn't change the temperature, times 298 Kelvin over, but now my new volume is 5.0 liters, right? And I get my pressure of helium under these circumstances is 9.19 atmospheres. Now, could I have accomplished the same thing simply by saying that the only thing that's really changing here is that I've got 46 liters being compressed down to 5 liters. If I divide 46 by 5, because this would cancel out and this would cancel out and the 1 wouldn't make any difference, 1.88. I'm wondering if 46 divided by 5 is also going to equal that.
Yeah.
Does it?
9.2.
Okay. So I probably could have just recognized that the only thing that I was really changing here was 46 to 5. And I could have just said, I could have just done this. Partial pressure of helium equals 46 liters divided by 5 liters. So the only thing that I was changing was the volume. I should put that in the form of a formula though. So pressure is going to equal volume 2 divided by volume 1 times pressure 1. And that would have been 1 atmosphere, right? Okay, that actually made it too easy. So equals 46 over 5 times 1 atmosphere. And that gives me 9.2 atmospheres. Okay, so we could have done the same thing that way, just recognizing that. So we could probably also do that for oxygen, couldn't we? I changed from 12 liters to 5 liters at 25 degrees, where my initial pressure was 1 atmosphere. So I'm going to say partial pressure O2 equals volume 2 divided by volume 1. Oh, actually I should have put that the other way, shouldn't I? Volume 1 divided by volume 2. Sorry. Okay. Yeah, volume 1 divided by volume 2 equals 12 liters over 5 liters times 1 atmosphere equals, and what do I get? 2.4. Atmospheres. Okay, and so I want to know what the total pressure is. P equals PHE plus PO2 equals 9.2 plus 2.4 equals 11.6. Okay, now I want to show you again the internal consistency here, so I want to go ahead and figure out how many moles of oxygen we had too. So if I figured out the moles of oxygen, again, that's going to be equal to PV over RT. The moles of oxygen was going to be 1 atmosphere times, there were 12 liters, divided by, oh, we're almost out of time, aren't we? 0.08206 times 298, and I'll stop using units. So 12 divided by 0.08206 times 298. So I have 0.491 moles. Okay, so I had 1.88 moles plus 0.419 moles of particles. So I have 2.371 moles of particles. And if I find out what the pressure just for that is, remember that's going to, pressure is going to equal nRT over V equals 2.371 times 0.08206 times 298 over 5 liters. So 2.371 times 0.08206 times 298 divided by 5 equals 11.6. Okay, so I want you to be aware of how very internally consistent this all is. Okay, so we'll continue on with partial pressures. So tell everybody there are good prizes
Okay.
if they play.
Well, it'd be bad prices for me because I'm allergic to peanuts. So that would have been actually.
Oh, sorry.
But no, it's. I mean, there's. Yeah. I didn't earn the prize anyway, so.
I have to say,